Welcome to another many-body gravitational simulation video. In this video, I present 3 scenarios that gravitationally collapse and evolve over 14 billion years. In each of these simulations, the average system density is approximately 5 times 10 to the minus 21 grams per cubic meter. For all 3 simulations, they begin with a collection of 160 of what I call extended objects. Each extended object contains 200 particles in them arranged in a Gaussian distribution. As we shall see, each of the simulations begins as a group of smudges like what you see here. What is different between these 3 scenarios is that the average density of the extended object in each simulation is different. In this case, it's about 1.5 times the average density of the entire system. This next scenario has an extended object density of about 2.7 times the density of the total system, and one can see this pretty much immediately since the smudges are visibly smaller. This final scenario has an extended object average density of about 18 times the density of the total system. Here the smudges are really small. While viewing these videos, please keep in mind that the XY plane is on the left and the ZY plane is on the right. Particle color is indicative of the direction it is moving. In addition, I have rotated the system so that its axis of symmetry aligns with the y-axis. Enough with all the talk, let's just get started. I love watching these scenarios collapse because I think they're extremely interesting, and I hope that you do too. All 3 of the systems that are presented will collapse in about 1 billion years. Watch for the creation of the particle halo and the particle blooming as the halo forms. Also notice that as the extended objects fall into the halo, they are tidally stripped, and that some of the cores survive that encounter. And finally, the halo interior doesn't change much after 7 to 8 billion years. The plot sequence we just watched had a scale of 800 kiloparsecs edge to edge. Let's zoom out to 3200 kiloparsecs edge to edge and see what the final distribution of particles looks like. I'd like at this time to point out some features of this particular view. First, we notice that on the edges here of this plot, their red-colored particles are traveling away from the distribution core, while the blue particles are falling back into the distribution core. Note that the white transitionary colors between the red and the blue mean that these particles are transitioning from moving away to falling inward. Let's examine the phase space diagram for this system. I like to call this plot the GRU plot because GRU has a shoulder, an arm, an elbow, a forearm, and sometimes fingers. Let's look closely at the characteristics of the phase space / GRU plot. First, in the upper right corner, there is a red box that I've outlined where particles are probably going to escape the system. Looking down the forearm, we see particles that may transition up into the red box area or may follow a trajectory down the forearm as they slow down and reach a minimum speed in the elbow, where they will gradually pick up speed and travel a trajectory up the arm towards the shoulder. It is very interesting to watch the evolution of the phase space diagram. This next sequence animates the phase space evolution. Watch during this sequence for how the extended objects fall in groups and then form the fingers of the plot. Also how the elbow forms and moves outward in time. The flow of particles from the forearm to the elbow and up the arm is also illustrated. And also note that there are secondary elbows. Let's now watch the next simulation collapse scenario. Here we have the extended object density as being 1.3 times 10 to the minus 20 grams per cubic meter. For this scenario, the extended object collapses in about 580 million years. The entire system collapses in about the same time as it took the previous scenario to collapse. As we watch this second scenario collapse, notice that it plays out very similarly to the previous collapsing system. Notice how the extended object cores collapse sooner, and more extended object cores survive encounters with the evolving halo. This is because the extended object cores collapse sooner, have more time to evolve to more compact forms, implying that fewer particles will experience tidal stripping. This is the final distribution, zoomed out now to 3200 kiloparsecs edge to edge. Here is the phase space plot for this simulation. Again, its features are similar to what we saw in the previous simulation. Note that there seem to be more particles in the finger areas, implying that there will be more particles escaping from this system. Notice that there is no distinctive second elbow in this simulation, as there was in the first. An interesting difference in this scenario is the vertical columns of particles. These columns correspond to extended object cores that have survived out to this period of time. There are many more such cores than there were in the previous simulation. Moving on to the final simulation that I am presenting in this video, this one with extended object densities of 8.7 times 10 to the minus 20 grams per cubic meter. For this simulation, the extended objects collapse considerably sooner at 226 million years, while the entire system is expected to still collapse within 1 billion years. In practice, the collapse of this system happens just a bit later at about 1.1 billion years. This simulation has many more extended objects surviving their encounters with the central halo. It is interesting to watch these halo objects orbiting the halo and survive many encounters with it. Clearly, these extended object cores are quite compact and thus can survive encounters with the halo. Here we have zoomed out to 3200 kiloparsecs edge to edge. Again, let's examine the phase space diagram. The phase space plot for the final simulation reveals that there are many more particles that have achieved escape velocity, as noted by the number of particles in the finger area. Also notice that there are more vertical columns this time, indicating there are more extended objects that remain intact after encounters with the halo. Here I present the final halo density profiles for these three simulations. Here are some things to note about this plot. The density profiles are offset by 1 decade each for clarity. Each simulation density profile is averaged over 375 time slices, which is about 250 million years, and centered at 13.8 billion years. The extended object with the lowest initial density has a halo with the highest density at its interior. For simulations with higher extended object densities, there are more particles ejected from the system. All three of these simulations exhibit a characteristic bulge over the expected NFW profile. This is common in many of my simulations, as they are co-moving isolated systems, unlike what appear in the literature. For these plots, I have removed the density offset. This makes the interior of each of the density profiles easier to examine. Notice how remarkably similar these three simulations are for distances greater than about 10 kiloparsecs. All three density profiles are shown with their NFW profile, but since they are all based on the virial radius, and that the virial radius is virtually identical for all three systems, the NFW profile is also consistent with that. The virial radius is a very useful tool for systems of interacting particles such as these. For systems that evolve like the ones presented here, the virial theorem tells us how these systems eventually change and evolve. The virial radius changes over time as the system evolves, and here you can see how the virial radius shows the collapse of the system and how the system eventually achieves the virial condition at around 4 billion years. See how all three systems collapse in about 1 billion years, and how the virial radius begins to drop around 7 billion years as particles are ejected from the system. Here we can also see time fluctuations in the virial radius as allowed by the virial theorem. I will finish the video with some notes on the simulations themselves. First, the total mass of the systems studied here is 1 trillion solar masses, or about the same total mass as the Milky Way galaxy. As noted earlier, the average system density for each of these three simulations is 5 times 10 to the minus 21 grams per cubic meter. Note that I use the definition of average density as the total mass inside the system virial radius. Each simulation has 32,000 particles arranged in 160 extended objects, each with 200 particles each. Each extended object is arranged in a Gaussian distribution. And as noted earlier, each of the 3 simulations has a different scaling radius for those extended objects. The 160 extended objects are arranged in an exponential distribution as shown in the equation below. Again, all particles begin the simulation with no kinetic energy, and all particles have the same physical size of about 0.2 of 1 kiloparsec. That physical size is used as a force softening distance. The force softening method used here is highly localized and is given by the equation shown in the slide. Hey, thanks for watching. If you made it this far, I hope you found it interesting and perhaps a little bit enlightening. And give yourself a pat on the back. This is your narrator, Rod Lund, signing out, and happy physics, everyone.